Okay, so MATLAB assignment number 3. The second question deals with a bank teller. Okay, a bank teller at a bank. Now, remember, MATLAB assignment number 3 deals with Markov chains. Okay, and you learned about Markov chains back in section 4.9. Okay, and you're dealing with probabilities. So just like with the first exercise from this MATLAB assignment, you have to also, for the second exercise, come up with a matrix. Okay, and in this problem, the second exercise, we have that a bank has a single teller. So this is a dated problem, obviously. But back when I was a kid, you know, when you needed to go to the bank, when you needed to get money, there were no ATMs or anything like that. You had to go inside the bank into a window and get the money from a teller. And there are still tellers at the bank now for certain things. How many have had to stand in line at the bank to see the teller, maybe for some reason, some kind of transaction you needed to do, and it required a teller at the bank? How many maybe have had that experience? Or maybe your parents have had that experience. Well, okay, Belen says in Ethiopia, that's how it's done. And Jacob said he uses his iPhone app. Okay, well, well, I will tell you, Bella makes an interesting point because I have a friend that lives in El Salvador, and she says also that tellers are common. So, but you know, it doesn't mean they don't have ATMs. But I'm just saying, in some countries, tellers are still fairly common. So, at any rate, you know what a bank teller is, and in this case, the bank teller, there's a queue that holds a maximum of n customers. In a unit of time, the teller will handle at most one customer, and at most one customer will attempt to join the queue, okay, in 1 unit of time. Let P be the probability that there's an arrival in the unit of time, and let Q equal 1 minus P. And let R be the probability that the teller finishes with the customer in a unit of time. Okay, so they say here, let S sub I indicate the total number of people either in the queue or being served is I. And there are n plus 1 states. Now here it says suppose that n equals 10. Suppose that n equals 10. If n equals 10 and it says suppose there are n plus 1 states, how many states do there have to be? 11. That's right, Mikhail. So this matrix, what's the size of it going to be? If there are 11 states in the matrix, and again, the state is the total number of people in the queue. Hold on, there was a comment here. Well, no. All right. So there's more information about probabilities and so forth. Okay, but like let's just take a look here at, you know, what would the matrix look like? What would the matrix start looking like? Okay, let me show you here. So what you're going to have to do is in your groups, just like with the first exercise, in your groups, you're going to have to come up with what this matrix is. Okay, but in this problem here, in this problem, you have a matrix. And there are 11 states. Okay, so the first state, hold on, let's get that a little, can never get this with the stylus. Okay, the first state is S sub 0. Second state, next state it is S sub 1. Next state it is S sub 2. Now what does S sub 0 mean, by the way? If the system, or if you're in state 0, if the Q is in state 0, that means, well, notice the 0 there. That means nobody is in line. Nobody's in the queue. So the teller's just sitting there. Nobody's in line. If the system is in state 1, you have one person in line. Right. That's right, Mikhail. That's how the states work. And how many states were there? How many states? 11. That's right. So that means that you can have up to how many people in line? State 10 means how many people are in line? Well, state 0 means nobody's in line. State 1 means, well, just one person's in line in the queue. State 10, how many people would be in line at the bank if we're in state 10? Ten. Good, Belen. Good, Marcella. 10 people. Okay. Now, what happens is, you see, we can transition from one state to another state. Okay, we can transition 0, 1, 2, 3, 4, 5, 6, 7, 8. I don't have enough room. Hold on. Do it again. Let's try it again. State 0, state 1, state 2, state 3, state 4, state 5, state 6, state 7, state 8, state 9, state 10. Okay. How many entries are you going to have to determine in this matrix? What are the dimensions? How many rows? That's right. 11 by 11. So there are 121 probabilities that you need to figure out here. But don't be alarmed, because some probabilities might be very easy to figure out. So you have to read the constraints of the problem and figure out what's possible. So for instance, let's say that state 0, let's say at a unit of in a unit of time, this is in a unit of time. Um, hold on here. Let me just make this a little better. Got to have this stuff kind of line up, you know. Yeah. So I'm making the dots just a little bit more, you know, a little better here. Okay, now let me do a little erasing here. To make things just a little nicer for you all. Okay. So, like for instance, let's say that you determine that going from state 0 to state 2, state 0 means there's no one in line. After a unit of time, can you go from nobody being in the line to 2 people being in the line? You have to determine that. But if the answer were no, if this were not possible, then this entry here, what would this entry here be? What would this entry here be? If this were not possible, if you have initially 0 people in line, and after a unit of time, the line can't become 2 people, what would this entry equal here? What value would you put in there? Good, Bellum. Good, Mikhail. A 0. Okay, well that means that the entries here and here, okay, if that's the case, and by the way, the rest of the entries would be 0 also, right? If you can't go from no people being in line to 2 people being in line, then you're not going to be able to go from no people being in line, you know, to 3 people being in line. So that's common sense. But let's say that you can go from no people being in line to, after a unit of time, no people being in line, or no people being in line, and then after a unit of time, 1 person being in line. What do these 2 entries here and here have to add up to? What do those entries are? Probabilities, right? Because this is a stochastic matrix. So what do those 2 entries have to sum to? What number? That's right, Mikhail. 1. That's right, Bellin. 1, because 1 is 100%, right? That's like all the possibilities. So what you have to do in this problem is you have to go through and figure out what all the non-zero probabilities are, and what the 0 probabilities are. And the way you're going to do that, of course, is you're going to have to, hold on here, you're going to have to hold on. One moment. You're going to have to work with all of the information given in the problem here to determine the probabilities. Okay, that's what you're going to have to do. And what I'd like you to do is in your groups, work on this, and then perhaps next week, maybe next Wednesday, when if I can have some work time in class, maybe I can come to your breakout groups and you can share with me what you think your probabilities are for like the second problem in MATLAB assignment 3 and the first problem, and I can let you know if they're right or wrong. How many think that would be kind of a nice idea for me to, would you like me to check your matrices? Okay, Mikhail says yes to that. Who else would like me to check their matrices? Okay, Bell and Wood, wonderful. Okay, all right. So I can do that. I can do that. And all right, so this now gives you guidance for this second MATLAB exercise. And on that note, I will stop the recording. Very good. So again, use all, make use of all this information in the problem to help you get the probabilities for the bank teller problem, exercise 2. Okay, wonderful, excellent.